Hello to everyone. This is an article with the title of Sensitivity Analysis of Stress, Pre-corrosion, Nanoparticles and Heat Treatment and Fatigue Lifetime of Aluminium Alloy, which will be presented by me, Mohammad Azadi, besides Hanieh Aroo from Faculty of Mechanical Engineering, Semnan University in Semnan, Iran. This article is presented in the International Conference on Fracture and Structural Integrity in Turin, Italy. Here you can see the abstract and the keyword of the article that will be introduced in next slides. For the introduction, I should say that we know about the advantages of aluminium alloy: good casting behavior, low density, proper wear resistance, and moderate thermal behavior. So because of these properties, we have different and a wide application for aluminium alloys. They have been vastly utilized in engine and automotive industry. But what is the problem? The problem is corrosion phenomenon, especially in combustion engines, especially in diesel engines, due to the presence of the sulfur in the fuel. And what is the working condition in this component? That is cyclic loading under environmental effect, including high temperature and corrosive fluid in diesel engine. So we need to check the corrosion fatigue phenomena in aluminium alloys. What is the research method here? The material is as-cast piston aluminium alloy that was casted in a cast iron mold by the gravity casting, but for the nanocomposite, we have used stir casting with 1% of nanoclay particle. The material chemical composition you could see in the table. The base is aluminium, and for silicon we have about 12 or more. For Cu we have 1, and for Mg we have also 1. But we have some nickel value because we want to increase the properties at high temperature. What is our corrosive environment? That is a sulfuric acid. That amount is 0.00235% that could be found in diesel engines. And here you can see the casting procedure that we have done it before. For fatigue testing, we have used pure bending fatigue testing based on ISO 1143. That is our standard. That is the standard that we have used under 4 stress levels: 120, 150, 180 and 210 megapascal by the SFT 600 rotary bending fatigue testing machine. And what's happened to our corrosion fatigue testing? We have done fatigue testing for pre-corrosive standard sample after 200 hours in the acid environment. Here also you can see the device, the machine, the testing machine, and also the sample before and after the pre-corrosion phenomena. You can see here some pits could be found on the surface of the sample due to the corrosion. For the sensitivity analysis, we have used Minitab software for the regression analysis. If you use the risk level as 0.05, then your p-value should be less than this selected risk level. And if you have higher f-value amount, it means that you have higher effect of inputs on outputs. So if the p-value was less than 0.05, so it means that your parameter, the inputs are effective on outputs. And what is inputs in our tests? Here is stress, pre-corrosion, nanoparticle, and also heat treatment. And what is the output here? Is the fatigue lifetime, both in normal and logarithmic scales. So we have some explanations and abbreviation for different material that we have used. Here you can find that for aluminum silicon alloy we have ILSI N0T0. It means no nano we have used and no heat treatment were applied. For aluminum silicon alloys reinforced with nanoparticle, the number is N1, but without heat treatment, so we have T0. For the aluminum silicon alloy reinforced with nanoparticle and the heat treatment, both N is 1 and T is 6. It means we have used a typical T6 heat treatment. For pure bending fatigue, we have used PF, and for the corrosion fatigue testing, we have used CF abbreviations. What is the results and the discussion? Here, for the first result, you can see the stress lifetime curves for both pure fatigue and for corrosion fatigue. If you have checked these curves, you can find that the nanoparticle heat-treated material, the heat-treated nanocomposite materials have higher lifetime. That was in green color lines, and here also we have the same behavior for corrosion fatigue. So under high stress level, the corrosion fatigue lifetime of aluminum alloys reinforced with nanoparticle and the heat treatment increased compared to the base material. This result could be also in the literature, reference number 1. For a better comparison, you can see here the pure fatigue curves besides corrosion fatigue curves. The first figure is for piston aluminum alloy, the second one is nanoclay composite, and the third one is heat treated nanoclay composite. Again, you can see a shift in all the results that we have for pure fatigue. So the corrosion fatigue lifetime of all 3 alloys was less than the fatigue lifetime. Such a behavior also was seen in the literature. For the regression analysis, we have used fatigue lifetime in a normal scale. So you can see the parameter, F value, P value, and R2, the coefficient of determination. You can see here the coefficient of determination is so low, it is not near 100%. So it means that the modeling, the regression analysis is not good and it's not proper. For the regression, we have p-value less than 0.05, so it means that the regression was meaningful. And here we have the stress and pre-corrosion are the effective parameters. Here you can see the Pareto chart. A is stress and D is pre-corrosion. 2 parameters are effective and 2 parameters including C and B, it means heat treatment and nanoparticle, have no any effect. But this is not correct because the coefficient of determination was low. If you use the logarithmic scale for the fatigue lifetime, you can see here the R2 value increased more. It's about twice time from the previous value. So here also we have a p-value, a proper p-value for the regression, and all parameters are now effective. From the Pareto chart you can see A is the most important parameter, has effect on output on the logarithmic scale of the fatigue lifetime, which is stress. Then D is important, it is pre-corrosion, then the heat treatment, and the last parameter which is also effective is nanoparticle reinforcement. If you have checked the behavior, the trending behavior of each parameter, each input on the output, you can see as expected, by increasing the stress, the fatigue lifetime decrease. By nanoparticle, that is an interesting result. With nanoparticle you have lower fatigue lifetime, but with heat treatment you have higher, and as expected pre-corrosion lead to lower fatigue lifetime. And this is the interaction behavior of different parameter on the fatigue lifetime. This means that when you have no cross lines, so there is no any interaction between these parameters, and they have separated effect on the fatigue lifetime. So for the conclusion, I want to say that the result of the fatigue test indicated that the fatigue and corrosion fatigue lifetime of the aluminum that was reinforced with nanoparticle and also heat treatment increased about 128 and also 140% under high stress, and compared to the base material. And also for the lowest stress level, this behavior was not seen. The lifetime reduction was more significant for 200 hours of the immersion time in the corrosive fluid. So this behavior was more significant with the high fatigue lifetime or lower stress level. The corrosion fatigue lifetime of all three materials was less than the fatigue lifetime. That was due to the surface damage and pits caused by corrosion reaction. And the result of the sensitivity analysis showed that all four parameters of stress, pre-corrosion, nanoparticle, and the heat treatment had an effective influences on the logarithmic scale of the fatigue lifetime. And you can see here the references that we have used, and for the acknowledgement I should thank MPN company located in Isfahan, Iran, for preparing the raw material. And if you have any question, you can email me that m_azadi@semnan.ac.ir. Thank you very much and goodbye.